Well, for this screencast, I am looking to help pull together the topics from 3 different chapters in our text here. In chapters 10 and 11, we were introduced to hypothesis testing. And in chapter 12, we were introduced to confidence intervals. And I'd like to take a look at one problem from each of the chapters, namely 10.5, 11.13, and 12.7, due to the fact that all 3 of them are focusing on the same scenario and the same set of statistics. But all 3 of them are taking a look at it from a different point of view. And I want to use this as a walkthrough to strengthen your understanding of each of these different approaches, but also point out the interconnectedness of them. So for 10.5, we had a hypothesis test here. We were testing to see whether or not the salaries for women faculty members were significantly different than a previously known average salary of faculty members in general. So we were given a population mean of 82,500 and a population standard deviation of 6,000. This was a previously known set of statistics here that we were using as our template. And then the problem went on to test whether or not investigator wanted to take a look to see if this held true for women faculty members as well. So the investigator wanted to test to see if there was a difference between the women faculty members and the previously known mean. And the word difference was important because this set up what's called a two-tailed test, or a hypothesis testing here that looked for a difference of means rather than less than or greater than. So there were a sample of 100 faculty members, female faculty members selected, and their mean was 80,100. So that it's obvious that this is different than the 82,500, but the question then is there a statistically significant difference? Is it so different that we do not think it's by chance, but we actually think that the mean of women is different than the mean that was previously understood? So our hypothesis testing here was set up as follows. And our alternative hypothesis test here is usually what the focus of the study is. So in this case here, our H sub A, or alternative hypothesis, is that the mean is different than or not equal to the 82,500 that was previously understood. Therefore, then, our null hypothesis is that the mean is the same as the original mean. And how that applies here then to normal curve is this. We have a normal distribution, and we know that the mean is 82,500, which is going to be right here. And the alpha level was 0.05, or our level of confidence or significance was 95%. Due to the fact that our alternative hypothesis was not equal to, we are then accounting for the possibility of our sample being significantly greater than or less than. We didn't have a caring of which direction. Therefore, our 95% are going to be centered about the mean here. Again, with 82,500, and our test is going to account for the possibility of it being significantly greater than or significantly less than our previously known mean. Therefore, then we use the table in the back of the book, and we know that a centered 95% here means that if we cut this in half, roughly 47.5% are going to be between the mean and this z-score. So we use that value to find out what our critical z-score is going to be, which is basically going to be our make or break point. And we do this prior to taking the sample. This is based on 2 things again. The fact that it's not equal to means that we're going to have 2 tails, and the 95% was given in the problem. And that gave us z-scores of negative 1.96 and positive 1.96 as our make or break points. Those are our critical values. Then we use the formula for the z-score for a sample mean, which is important that you know that it's a sample mean of a population, not of an individual score. And that z-score then is our sample mean, which was the 80,100, minus the previously known mean, which was 82,500, divided by 6,000, which was the standard deviation, divided by the square root of 100, 100 being the sample size. This is a critical point right here that you do this. The direction here of your subtraction is important also. Notice that we have the sample mean in front of what the population mean was. This allows us to get either a positive or negative z-score depending on whether or not our sample is less than or greater than the population mean. Since it was less than, we want a negative z-score. So make sure you subtract left to right. All of this then produced a z-score of negative 4.00, which if we plot it on the normal curve here is going to be way out here on the tail, much further left than our critical value of negative 1.96. And since it fell outside this window here and further out in the tail, we then reject the null hypothesis. And this is evidence to show that the population of women faculty members is significantly different than the population that we had previously known. So we rejected the null hypothesis. Hopefully that helps surmise 10.5. For 11.13 or 11.13, the difference here was that the investigator wanted to see if there was discrimination against women. And therefore, then, our concern is not that it's significantly different than the mean, but are the women faculty member salaries significantly less than? So our alternative hypothesis here changed to a less than 82,500 versus what was over here significantly different than. And since this is less than, our null hypothesis technically needs to change from not being equal to 82,500, but being greater than or equal to. Notice that these two values, or these two symbols, inequality symbols, need to together make sure we cover the entire population. So since we're taking a look again at the alternative being significantly less than, so we're only taking a look at a tail on the lower end rather than two tails. So this is now a one-tailed hypothesis test. And we focused all of our percentage of being outside this 95% towards the one tail. And the question in the text asks if we wanted to make sure, a little bit more sure of ourselves for this hypothesis testing, then they kind of were leading you to select a lower level of significance, because the textbook kind of was leading towards the idea that if our sample produced a mean low enough, then it would possibly lead to very expensive litigation. Many of us in our responses said that we should change this to 1%. That would be if you were trying to avoid the litigation. But some people might take a look at it a different point of view and say, you know what? I still want to have a 95% level of confidence or a 5% chance of error here. I think it's worth more in the long run ethically to produce a value that shows that the women were getting significantly less money than men. Maybe we're not too worried about the litigation costs. So I guess this would depend on your point of view, not you personally, but if the statistics were going to be used by the litigation lawyers, maybe they would make it 1%. But if you're an activist trying to prove that women were getting paid significantly less than the general population or the men, then 5% might be the value that you want. In either way, notice then our critical t-scores here change. If 5% was still going to be our alpha level, then we're looking at 5% all here on one tail, which produced a negative 1.645 z-score, critical value. But if we're looking at 1% all the way on the tail, then our z-score, or critical z, increased or went further out to a negative 2.33. Either way, our value of negative 4, which was based on a sample of these 100 women, was still further out in the tail. And either way, we can reject the null hypothesis. Hopefully that then reviews 11.13 well to you. And that leads to 12.7. 12.7 is in the chapter focusing on confidence intervals. And this was not one of the items in the textbook for our assignment, but I'd like you to take a look at 12.7. It basically is saying, take a look at the same information that we have here from the previous two problems, but instead of setting up a hypothesis test, we are then instead constructing a 99% confidence interval for the mean salary for all females. And what that means is this. If this random sample of 100 females produced a mean of 80,100, then what can we say about the entire population of women? Not all men and women, but of all women. 80,100 is our best point estimate, because that is the sample mean of our 100 in the sample. But we're going to add and subtract a margin of error here in order to give us an interval that contains what we think is the true mean. Again, think logically here. We randomly selected only 100 women. The chances of that being the exact population mean of all women is pretty slim. However, that is our best guess here, 80,100. And what we're going to do then is apply a margin of error to that. And we use this formula for confidence interval, which is in the end there of chapter 12, which is the sample mean plus or minus the z-score that is associated with our level of confidence times, and you'll notice here, this is the same as the denominator over here. It's our population mean divided by the square root of the sample size. So from the information, the sample mean here is 80,100. I'm going to add and subtract the margin of error here of 2.58. This 2.58 comes from the 99% confidence interval, which comes from, in the back of the textbook, if instead of this 95% being here in the middle, we're going to increase this to 99%, which means our critical values are going further out towards the tail. And we're splitting up the 1% error to 0.05. And if we look in the back of the book, the value that gives us an area of 0.05 in this point here, and 0.05 to this point, is 2.58. So that is our 99% confidence interval z-score. And then again, I'm multiplying this to the 6,000 divided by square root of 100. All of this then again is being added and then separately subtracted from 80,100. And you'll notice here, 80,100 is between exactly these two values. When I did 80,000 plus this, I got 81,648. When I did 80,000 minus this value, I got 78,552. And how that is interpreted is this. Based on our sample of 100 randomly selected females, we can be 99% confident that this interval from 78,552 to 81,648 contains the true mean of all women faculty members. I'm 99% confident that the true mean is going to be somewhere within these two values. Therefore, then, since 82,500 is outside of this interval, then it kind of supports the idea that we reject the null hypothesis and that the mean for women is different than the 82,500. And we suspect it at a 99% confidence that it's between these two values. Hopefully this screencast helps connect these important statistics of hypothesis testing and confidence intervals.